Welcome back to AERO 1020, Theory of Flight, presentation number 19 on weight and balance. If you were to ask someone on the street with no aviation experience about a typical single-engine piston aircraft with 4 seats, that person would probably assume that the pilot could fill the aircraft with full fuel and 4 adult passengers and a full luggage compartment with no problem, because that's what the aircraft is designed to carry. But that's not always the case. In this presentation, we'll discuss weight and balance and why it's important to determine the weight and balance of an aircraft. We'll discuss the 2 issues, total weight and the balance of that weight. And we will go over important definitions, important for you to understand in determining the weight and balance of an aircraft, and how to calculate the center of gravity position. You recall that one of the 4 forces acting on the airplane in flight is weight. We have to consider the total gross weight of the aircraft, because a heavier aircraft requires more lift to fly. And there are limits to the weight. Here's a picture that demonstrates why it's so important to calculate your weight and balance before you take off in an aircraft. It appears that this aircraft may be loaded heavier than its maximum gross takeoff weight. It appears that it just got off the ground right before the end of the runway, and it may have a problem clearing that mountain. Before we move on, let's go over some definitions that are important for you to know in order to understand all of the issues surrounding weight and balance. The first definition is maximum gross weight. And maximum gross weight is a limit on the aircraft that includes the basic empty weight of the airplane, which is specific to a specific tail number, the pilots and the crew, passengers, baggage and cargo, and fuel. The basic empty weight includes the weight of the aircraft, and again that's specific to that tail number, all permanent installed equipment in the aircraft, hydraulic fluid, usable fuel, and normal oil level. The useful load excludes the aircraft's basic empty weight. So it's everything except for the basic empty weight, the pilot and the crew, the passengers, the baggage and the cargo, and the usable fuel. So in other words, it's stuff we can take on and off of the aircraft. The basic empty weight plus the useful load equals the gross weight. The payload includes the useful load minus the usable fuel. Zero fuel weight is everything except for the weight of the fuel. Let's look at some limitations on weight and balance. The first one is maximum takeoff and maximum landing weight. It appears that the aircraft in this picture may have a weight and balance problem. In the Pilot's Operating Handbook or the Airplane Flight Manual, you'll find limitations on weight and balance for any aircraft. In this picture you can see the weight limitations in the Pilot's Operating Handbook for the light jet called Phenom 100. Notice that the maximum ramp weight is slightly higher than the maximum takeoff weight. That's because it's assumed that fuel will be burned during engine start, taxi, and run-up before the aircraft ever takes off. Also notice that the maximum landing weight is significantly lower than the maximum takeoff weight. That's usually not a problem because the aircraft will burn fuel during the flight and should weigh less when it's ready to land. However, what if there's an emergency right after takeoff, maybe a medical emergency, and the aircraft has to return to the airport immediately? That could present a problem. Now, some aircraft are equipped to jettison fuel when that happens, but not all aircraft have that capability. So the aircraft may not be able to return immediately for an emergency landing if they are over the maximum landing weight. So while weight limitations are important, it's not the only thing that we need to be concerned about. We also need to be concerned about the balance of that weight in the aircraft. The balance, or the center of gravity position, or CG position, is very influential when it comes to longitudinal or pitch stability. Before we move on to look at calculating weight and balance and the center of gravity, we need to define some terms: weight, which is a force, the arm, moment, center of gravity, and the reference datum. Remember, weight is just a force, and it's a force due to gravity. The arm is the distance from an applied force to a pivot point. And you can think of different size wrenches, each with different length handles. The wrench with the longest handle is going to have the most force. So think of that handle as the arm. The longer the arm, the larger the applied force, which is known as the moment. So again, the moment is the resulting force, either pitching or twisting force. And it's the product of the force times the arm. So in weight and balance terms, weight times arm equals moment. Now there are two calculations that you need to remember and understand when calculating weight and balance. And weight times arm equals moment is the first one. The center of gravity is where the weight of the aircraft is concentrated or focused. If you were to suspend an aircraft from the center of gravity, it would balance perfectly. It's important for the pilot to know where the CG is because the airplane pitches, rolls, and yaws around the center of gravity. Think about a seesaw with a heavy weight on the left and a lighter weight on the right. In this condition, the heavier weight is going to drop to the ground. The weight is not balanced on either side of the fulcrum. So how can we balance the seesaw without changing the weights? Well, we can move the lighter weight further away from the balancing point or from the fulcrum. If we move the 20-pound weight 100 inches from the fulcrum, we're increasing the arm. And remember, arm times weight equals moment. So 100 inches times the 20 pounds equals 2,000 inch-pounds of force. That equals the force being applied on the left side of the seesaw because the 100-pound weight is only 20 inches from the balancing point or the fulcrum. So the weight on the left is also applying 2,000 inch-pounds of force. So what is the fulcrum? The fulcrum is the balancing point. So how does this apply to an airplane? How do we compare the fulcrum on a seesaw to the weight and balance problem on an aircraft? Where is the fulcrum on an aircraft? Well, the answer is at the center of pressure, or the center of lift. That's where the fulcrum is. The center of gravity is in front of or forward of the center of pressure. You can think of the center of gravity as the weight on one side of the seesaw and the tail down force, or the force provided by the horizontal stabilizer on the tail of the aircraft, as the weight on the other side of the seesaw. So which of these forces can we move? The center of pressure, remember, moves forward and aft on an asymmetrical airfoil based on the angle of attack. So we can move the center of pressure. We can also move the center of gravity through different aircraft loading and also fuel burn. The position of the center of gravity, or the CG, has an incredible effect on the longitudinal stability of the aircraft. Remember, longitudinal stability is stability around the lateral axis, and that's pitch stability. What happens to the tail downforce required if we move the center of gravity forward or further from the fulcrum? Well, we require more tail downforce because we have increased the arm from the center of gravity back to the fulcrum, and that requires more tail downforce to overcome. The opposite is true if we move the center of gravity aft or closer to the pivot point. If we do that, we'll require less tail downforce because we have reduced the arm between the center of gravity and the pivot point. If we move the center of gravity so that it is exactly at the fulcrum, then no tail downforce is required. Aircraft are designed with limitations on the center of gravity. There's a forward limit and an aft limit, and within that limit is the acceptable range for the center of gravity. If an aircraft's center of gravity is at or beyond the forward limit, you have a nose-heavy aircraft. However, that aircraft is also very stable because the arm from the center of gravity back to the tail downforce is longer. And remember, a longer arm results in more force. So more tail downforce is required, which means that the pilot will have to fly at a higher angle of attack. Because the pilot needs to fly at a higher angle of attack, more load is being generated. And remember, more load leads to higher stall speeds. If the CG is at or beyond the aft limit, in other words, it's closer to the pivot point, you have decreased longitudinal stability. It's not as stable as an aircraft with the CG at the forward limit. The arm from the CG back to the tail downforce is shorter, so less tail downforce is required. So the airplane can be flown at a lower angle of attack. And because it's at a low angle of attack, it's generating less load, and less load leads to lower stall speeds. A tail-heavy aircraft, though, has poor stall characteristics. Because the aircraft is tail-heavy, the pilot may not be able to push the nose down to recover from a stall or a spin. So how do we determine the center of gravity? Well, first, we need to know the weights and the arms to determine the moments for each load item. The arm is the distance from a reference datum back to the load item. The reference datum is an imaginary line that the engineers have designated in order for you to be able to calculate the arm and then use that distance to calculate the moment. Every aircraft has a different reference datum. Here is the reference datum for the Diamond DA-40. Notice that it's out in front of the spinner. In this figure, you can see that the reference datum is located behind the propeller, actually behind the engine and just in front of the firewall. The reference datum for the Diamond DA-20 is actually inside the cockpit. And the reference datum for the Piper Cherokee, pictured in this slide, is just in front of the spinner. The datum for the small jet pictured in this slide is right in front of the nose of the aircraft. In this figure, you can see the datum location for a large transport category aircraft. And again, you can see that the datum for the Diamond DA-40 is out in front of the spinner. The distance from the datum back to the pilot and the co-pilot is 90.6 inches. The distance from the datum back to the fuel is 103.5 inches. And the distance from the datum back to the rear seat is 128 inches. To determine the center of gravity, we need to calculate the moment of each item in the aircraft by taking the weight and multiplying it by the arm. When we get all of those moments and all of those weights, we can add them together to get the total weight and the total moment. To determine the center of gravity, we take the total moment and we divide it by the total weight. Once we determine the center of gravity position, we can plot that on a graph to determine whether it's within the weight and balance limitations. So what if it's not within the weight and balance limitations? What if we need to shift weight so that our center of gravity is acceptable? Well, we could shift the weight and do all of the math again, or we could use the weight shift formula. The weight shift formula is weight moved divided by the total airplane weight equals the distance that the CG will move over the difference in the arms. So let's assume that the center of gravity is beyond the forward limit. To resolve that, we could move some weight from the front seat to the rear seat. Instead of doing the entire weight and balance calculation again, let's try the weight shift formula. We could move 200 pounds from the front seat to the rear seat. Let's assume that the aircraft weighs 2,950 pounds. And the difference between the front seat arm and the rear seat arm is 37.4 inches. So the calculation would be 200 divided by 2950 equals x, which is the distance that the CG will move, divided by 37.4, or the difference in the arms. Well, let's divide 200 by 2950 first. We'll get 0.0677966 equals x over 37.4. Now we can solve for x by multiplying both sides by 37.4, and we get x equals 2.5356. So that would be the difference, or the distance, that the center of gravity would move if we were to shift 200 pounds from the front seat to the rear seat. Well, that's the end of presentation number 18 on weight and balance. The next presentation, 19, will be on load factor.